Good morning to all. We are waiting for the today's speaker, Professor Suman Chakarborty from ADIT Kharagpur. We are trying to contact him and probably he will join very soon. So once again, welcome to the second day AICT AQIS sponsored faculty development program on computational fluid dynamics for engineers. So kindly wait for some time till our speaker will join to the session. Thank you. So very good morning to all. We have received the message from Suman Chakravarty said that he is joining very soon within 5-10 minutes. So please wait. Thank you for your patience.
Good morning, all of you. So our today's speaker, Dr. Suman Chakravarty, sir, has joined. Good morning, sir.
Yeah, good morning, and it's a pleasure in joining this. Good morning to all the participants.
Yes, sir. I would like to request Dr. Mitesh Shah to introduce our esteemed guest for this session today. Over to Mitesh Shah, sir.
So once again, very good morning to all and very warm welcome to today's speaker, Professor Suman Chakravarty sir, by Department of Mechanical Engineering of AD Patel Technology, a constituent college of Charotar Vidya Mandal University, located in the milk city of Anand in Gujarat. So this is today is the second day of AICT AQIS sponsored faculty development program at Gujarat, and we have invited Professor Suman Chakravarty from IIT Kharagpur in this virtual meeting. Before we start this session, I would like to introduce him briefly. Very rich profile, sir, very prestigious speaker we got today. I would like to introduce him. Professor Suman Chakravarty is currently working as a professor in Department of Mechanical Engineering at IIT Kharagpur. He is also Dean of Sponsored Research and Industrial Consultancy in IIT Kharagpur. He was formerly the head School of Medical Science and Technology during 2015 to 2019. Also, he was Indian National Academy of Engineering Chair Professor in 2014 to 16. He joined IIT Kharagpur in 2002. He appeared for the national level competitive exam, namely GATE examinations in 1997, and he was a topper in that examination. This is a really prestigious matter for everyone. He joined the IISc Bangalore for his master's study, where he was the topper, and he got 7.9 out of 8 CGPA. He received gold medal and Senate commendations for outstanding performance in Master of Engineering. Thereafter, he joined Jadavpur University as a lecturer in 2000. He joined the IISc for his doctoral research on study leave from Jadavpur University. He completed his PhD thesis work in about 1 year at the IISc. He received Best International CFD Thesis Award in 2002. Dr. Chakravarty has research interests in the area of microfluidics and micro-nanoscale transport processes, including their theoretical, computational, and experimental modeling, encompassing the underlying fundamentals as well as biomedical, biotechnological, cheap cooling, and energy-related applications. Professor Chakravarty is known for his fundamental as well as translation research in the domain of microfluidics and nanofluidics. He has published 400 plus papers in international journals of high repute. More than 30 PhD students have graduated working under his supervision, guided or co-guided by Professor Chakravarty. Professor Chakravarty has authored several textbooks and edited several research monographs. He has also developed several video lectures, courses under the national programs on technology enhanced learning. Professor Chakravarty has also been the editorial board member of journals in his field of expertise, including scientific reports. He has received one of the most prestigious awards, which is known as Shanti Swarup Bhatnagar Prize, and become the youngest fellow of the Indian National Academy of Engineering. He is a fellow of the Indian National Science Academy, Indian Academy of Sciences, Indian National Academy of Science. In addition of being the recipient of the Indo-US Research Fellowship Scopus Young Scientist Award given by the Elsevier for high citations on his research publication, Alexander von Humboldt Fellowship in 2005 he received, and Young Scientist, Young Engineer Award from various national academics. He has been bestowed with the Fellowship of the American Physical Society, Fellowship of the Royal Society of Chemistry, and Fellowship of the American Society of Mechanical Engineering, that is ASI. He was a visiting professor at Stanford University in the year 2018. He has been JC Board's National Fellowship, which is the highest fellowship awarded by the Department of Science and Technology of the Government of India. Dr. Chakravarty has received research funding from the various government and private bodies, including international funding agencies such as the British Council, Royal Academy of Engineering UK, Indo-US Science and Technology Forum, JSKS, Japan, etc. He has spearheaded the healthcare domain of Imprint India initiative as the national coordinator. He has also been a consultant to industrial houses such as General Motors, Delphi, Intel, Shell, Tata Steel, ITC, to name a few. He has also led his own startup company to effectively translate his research into the design of medical products. The objective of his company is to bring out novel devices for low-cost medical diagnostics. It's really a very exhaustive profile, very rich profile, sir. We are really fortunate to have with us. We had a lot of across the nation faculty members as well as research scholars are participating this particular FDP. Professor Anil Date sir is also welcome for this particular FDP. He is also a participant. Sir, I request you to start your session. Thank you, sir.
Good morning to all the participants, and especially I see Professor Date, legend in Indian. Why should I say only Indian? I mean, in the global arena, he's a legend in computational fluid mechanics. All of us, I mean, when I grew up as a student, my professors were his students. So, I mean, all of you can understand that. I mean, the people from whom I learned the subject were either his, I mean, some of them were maybe his undergraduate students, and I mean, one of them, I mean, with whom I interacted a lot during my stays in Germany, Professor Subhasis Ray, was his direct PhD student. So, I mean, it's a great honor. You will not understand, like, say, being a current cricketer, if somebody is, having, a performance where maybe, Sachin Tendulkar or Sunil Gavaskar is sitting, I mean, it's a special honor. So, I mean, my all regards to Professor Date, and I'm so glad to see that he's doing fine and taking his time out of the busy schedule to be a part of this meeting. And with all my best regards to such legends in Indian academics, because of whom actually, all the knowledge has passed on to the younger generations like us, and we are passing, of course, whatever we have learned to our students. This entire legacy started with, at least in the CFD domain, started with Professor Date, and of course his other illustrious colleagues. Prior to this, CFD was not, Indians knew CFD, but the way in which CFD is practiced today, that vision was not present prior to the era of Professor Date and other legends. So thank you, sir, so much for being with us. It's an honor. And with your due permission, I will start, I will upload and start my presentation.
Yes, please, sir. You can share your presentation.
Okay, sure. Somehow what always happens in Google Meet is, first time I cannot share. So what I will do is that I will log out of the meeting and again join, so that it works sometimes in my computer. So I just leave and join. Don't worry about this.
No, sir. No issues.
So I hope the presentation is visible. One of you can please confirm that it is visible.
Yes, sir. It is visible.
Okay. So let me start the discussion, and I want to give you a little bit of background of what I am going to present. CFD is, of course, an ever-growing area, and CFD has clearly many aspects. One is the mathematical modeling of the physical problem. The second is translating that into numerical computation. And third is, of course, developing further algorithms for advancement, including inclusion of new applications. So all these are parts and parcels of CFD research. And what I'm going to talk about today is one such aspect where the fluid dynamics of multiple phases is of purview. Traditionally, fluid dynamics of single phase was the area with which both theoretical as well as computational fluid dynamics evolved. All the standard algorithms for solving the Navier-Stokes equation and equations of similar prototype were fundamentally based on the traditional single phase flow features. But subsequently, it was realized that the entire world of fluid mechanics is flooded with multi-phase flow problems, and these situations are getting more and more different as the purview of fluid mechanics, material science, and micro and nanoscale transport, they are all converging together. And this perhaps required a new outlook or a different outlook based on which the CFD in these applications could be conducted. Multi-phase flows are parts and parcels of physical, natural, and engineering systems. One of the classical problems which we are talking about here, I mean, this I am showing at the very beginning for a particular purpose, that the entire concept of phase field modeling, which I will be talking about today, it started evolving around these types of applications where you have solidification of maybe a small crystal in a undercooled melt, and if you see or look into it microscopically, you can see various morphologies of growth. This is one particular morphology of growth which is called as dendritic growth, and this dendritic growth on a small scale is very important because on a larger scale it affects the structure of the material, microstructure of the material, the properties, and hence the performance in real industrial practice. So understanding the fluid flow, heat transfer, and mass transfer around these happen to be critical, and people have traditionally used very special materials based models to understand the phenomenon. In different aspects of engineering where traditional mechanical or chemical engineering aspects are more conspicuous, we are confronted with air-water flow through tubes and channels, very common in process engineering, industrial pipeline transport like slurry flows, cavitating flows, and flow through heat exchangers. This is part and parcel of engineering work, and more so in mechanical engineering and chemical engineering, of course. There are more complicated situations where numerical computation is somewhat more challenging, and I will tell you the exact reason why. So you see, for example, atomization and spray of a pulsed liquid jet. So when you see this, look at various fluid structures, so to say, or flow structures that are formed. On a large scale, you have a system, characteristic system scale. On a small scale, these are almost like sizes of of course not molecules, because we are not directly visualizing molecules here, but at least orders of magnitude smaller than the system length scale, which typically converges closer to the interfacial scale. So you have a complex hierarchy of scales here, and that makes it extremely difficult to capture until and unless you do direct numerical simulation, and that itself has its own computational challenges. In the domain of microfluidics in general, and its biological applications in particular, there are other obvious challenges, and these challenges are very critical and important because these are emerging topics, and my area of research over the past decade or so has been centered around these topics. So in microfluidics, dynamics of droplets and bubbles is very important. Not that these are important only in microfluidics, but in microfluidics, these have special implications because these have certain specialized applications like emulsion processing, oil recovery applications, very important for oil industry, and in general droplet microfluidics, where droplets are used as microreactors, micro mixers, or even drug delivery agents in the medical domain. In the biological world, multiphase flows can have extremely complex facets, which commonly as engineers we do not come across. See this typical example of blood flow through a narrow constriction. This is extremely critical to understand the physiology of certain cardiovascular diseases. So what is happening across this narrow constriction is that these red blood cells, which are extremely deformable in nature, they are migrating and deforming, and doesn't matter whether you capture the red blood cells explicitly, even if you apply a rheology model, the rheological model should be sensitive to these deformation dynamics, and that can actually give rise to a better physiological understanding of certain diseases and also disease detection technologies. So all these relate to very complex, starting from relatively simpler to extremely complex multiphase flow dynamics. I will try to start with a very simple description of the problem without getting into computation, just a fundamental physical description. And for that, we consider a simple case of two fluids which are incompressible Newtonian, and we have not considered any additional body force, because if there is an additional body force, what happens, that we will see subsequently. So summarily, you have incompressible Newtonian, individual fluid properties are constants. So such special case is there for the fluids 1 and 2, and you have an interface. Forget about the numerical computation. If you intended to apply a particular boundary condition at the interface, the boundary condition has to be hallmarked with the following. One is continuity in the velocity. This is number one. The second, so this is one of the kinematic constraints. The other kinematic constraint is the kinematic boundary condition, which is the second interface condition that I have mentioned in the box. So imagine that the interface is described by a function f, which is a function of the position vector x and the time t. Physically, a particle, we may imagine a fluid particle, no matter how complex is the interface deformation, the particle will remain at the interface. So if somebody is sitting at the interface and looking into the particle, the observer will observe that the particle is there on the interface at all times, which was earlier there. That means the total derivative of f happens to be 0. So that total derivative is decomposed into the unsteady and the convective component, and that is how the second boundary condition is written. This is known as kinematic boundary condition. One special version of this boundary condition, when applied over a solid boundary, is a no penetration boundary condition. So the first two boundary conditions for special cases of a fluid moving over an impermeable no slip solid is no slip number 1 and no penetration number 2. These are kinematic constraints and not necessarily related to any external or internal force. The third and fourth are related to the forces. The third one is the tangential force balance across the interface. So if there is no source of tangential shear at the interface, there will be a continuity across the interface for the tangential shear or the tangential force. And the last one is the normal force balance. where the jump in the normal stress is accommodated via the surface tension force and the interfacial curvature. This jump boundary condition is related to the normal stress, which is related to the hydrostatic component of the stress as well as the viscous normal stress. So this is the problem description in a fundamental sense, where the numerical computation or even a theoretical depiction of this problem is challenging, is that this interface, until and unless it's a rigid solid boundary, this interface function f, it evolves as a part of the solution of the problem and therefore is not known a priori. So this dynamic evolution of the interface has to be known and has to be linked with all these boundary conditions, and the domain of fluid 1 and fluid 2 will change accordingly. So we can all appreciate that this is a very complex conceptual problem and it can be tackled in many ways. The one possibility is that fluid flow equations are solved in both sides of the interface with matching boundary condition at the interface. So this is like explicit interface tracking method, where the fluid fluid interface is tracked explicitly, not implicitly, by employing Lagrangian grid points. This is a moving interface or moving mesh method. Traditionally, this has been very popular and very fundamental also, because it gives rise to extremely accurate calculation of the surface tension force because of a very direct capturing of the interface. Currently, a variant of this method known as boundary element method is extremely emerging and popular and is being used in many situations. Where research is still going on and the challenge remains is that when you have a large deformation of the interface, it can cause mesh entanglement. So, physically what happens is that under such situations, the Lagrangian grid points which are tracking the interface, they can get collapsed. So for that extreme topological change, like for example breakup, coalescence, etc., the numerical treatment gets very, very difficult, and it requires special attention. While there is a continuous activity in research to take care of all these, there are substantial scopes of improvement where these aspects can be taken into consideration to represent practically realistic situations of breakup and coalescence. The fixed grid method is an Eulerian framework where you conceptually have a single domain with a single set of governing equations, but you have a mathematical function that implicitly captures the interface. The mathematical function is conceptually related to the function that depicted the interface and in the kinematic boundary condition, but are mostly mathematical and artificial in different ways. There are well-known variants of these, like the phase field method, the volume of fluid method, level set method. Out of these, the volume of fluid and level set are extremely well established. They have their advantages with no special treatment required to simulate the topological changes, because the interface is not directly tracked, but it is implicitly captured through a mathematical function. But every advantage is associated with certain disadvantage. The disadvantage is that an extra equation has to be solved. Not only that, there are challenges related to satisfying mass conservation. This is an extremely challenging aspect which has been bothering researchers for a long time, and it still keeps on bothering. So out of these different variants, the phase field method is conceptually somewhat different from the volume of fluid or the level set. The phase field models, what they do is they replace the sharp interfaces separating the fluids or materials, whatever, by a diffuse transition layer. So this diffuse transition layer is an artificial layer because it is not directly capturing the atoms or molecules. So it's an artificial layer where the interfacial forces are smoothly distributed as volumetric forces. And similar thing is done for the continuum surface force methods like VOF or level set. But those methods are based on a direct use of surface tension as a force, whereas the phase field method is based on the description of a thermodynamic free energy. In the phase field method, the features of VOF or level set, so far as computations go, all those features are relatively similar, but the physical aspect is different, that the entire formulation evolves from thermodynamics by relating to the free energy of the physical problem, and therefore it is enforced to be thermodynamically consistent. It gives a physically realistic description when the interface width is comparable to the length scale of the phenomenon. And that is why for breakup, coalescence, or different complex morphological evolution over small scales, that is where this model is, it can find a high level of applicability. And the framework of this model can be extended to more and more complex problems, provided the problem is thermodynamically understood. The phase field model or method, it is developed based on one key parameter which is called as the order parameter or the phase field function. It is defined as following, whatever is there shown as a representation formula: N2 minus N1 divided by N2 plus N1, where N1 is the number density in phase 1 and then N2 is the number density in phase 2. So in phase 1, N1 is 1 and N2 is 0. In a mass fraction or volume fraction sense. So then in phase 1, phi is minus 1. Similarly in phase 2, phi is plus 1. So across the interface of phase 1 and phase 2, there is a transition of phi from minus 1 to 1. And that transition is not abrupt, but is implemented by a smoothing function that follows from the physical description of the problem. That is what is the essential physics of the method. Now, where the physics comes in is the free energy of the system. Here we are taking two phase as a system, is a combination of the bulk free energy representing the energy of the homogeneous phases far away from the interface, and a gradient free energy, which is the blue colored term, which is there at the interface only. Here lambda is a energy density parameter. We will talk about this subsequently. But the most important observation from here is that the blue colored term is a function of the gradient of phi, which exists only across the interface. This means that this is important at the interfacial region, where the red colored term is important in the bulk region. The bulk free energy, I mean, there are many mathematical fits to the physical description of the bulk free energy. One such very commonly accepted mathematical fit is the double well function, which is shown here both graphically as well as mathematically. If you see that this function has two minima, one at -1 and another at +1. Minimum of free energy represents its equilibrium configuration from thermodynamic viewpoint. So at -1 and +1, the equilibrium configuration is there, which means that it is capturing the fact that the bulk phases far away from the interface, if they are in equilibrium, this mathematical function is able to capture that properly. Now the total free energy is a sum of this bulk and the interfacial energy. The chemical potential is obtained by taking the variational derivative of the free energy, and that is done by using the Euler-Lagrange equation, very commonly known in variational calculus. This chemical potential is a physical depiction of the driving force of any chemical change to take place. So that chemical change takes place because of certain activities across the interfacial region, and those activities in a conceptual depiction, if you see this picture, this is diffused over a length scale of the order of epsilon. The classical sharp interface considers it macroscopically sharp. The phase field smears this over this of the order of epsilon, but if this epsilon is itself very small as compared to the length scale of the system, then it when the result is represented over the system scale, this will also appear to be visually very much similar to a sharp interface description. Although if you zoom it up at the interface, you will see this smeared representation. The total free energy, as you see here, is a combination of the bulk and the surface energy. For a one-dimensional problem, which can be analytically solvable, I am trying to give you a simple analytical derivation with an objective of how to relate the physical concept of surface tension with the free energy description that we have just come up with. Surface tension can be perceived as energy per unit area in the present purview free energy per unit area. So if you just integrate this across the interface and find out the energy per unit area, it will give the surface tension coefficient. So to do that, you first have to know or solve the function f, and then use that function in the integral which is expressed here. So to solve for f, we use the condition that for equilibrium, the chemical potential is constant everywhere, because I have just mentioned that the chemical potential physically is reminiscent of the driving force for a chemical change to take place. That means that if the chemical potential is constant, there is no net driving force. For reference, we can set that constant to any value, just like a datum for calculating the potential energy. Similarly, we can use as a reference or a datum. The datum we set as 0, and then we solve this with the appropriate boundary conditions and come up with this very interesting function. This is a natural smoothing function. Even if somebody considers purely from mathematics considerations, this is an excellent smoothing function, the tan hyperbolic function, which smoothens out the change of phi of -1 from one phase to +1 to another phase. You can see this, how nice this smoothing function is. Once this function is, this phi is substituted in this expression, you will see a relationship between surface energy and the mathematical parameter lambda that came with the free energy model, and the epsilon, which is a length scale characterizing the interfacial thickness. So if these are known, I mean this one from the rather the surface tension being known from the physical perspective, epsilon being known from the physics of the problem, that is what is the length scale over which the topology evolves in the problem. From this expression you can get a value of lambda, and that you can use in the numerical computations. Now, so far what I have described is very fundamental but not directly connected with fluid mechanics, because that described equilibrium. Fluid dynamics considers deviation from equilibrium. So when there is a deviation from equilibrium, the free energy does not remain constant, but the free energy evolves with time. But the hallmark of any natural system, no matter it is physical, chemical, biological, whatever, that the free energy must decrease with time. So I want to give you a pointer here. Actually, what I meant in terms of the engineering way of, or I should say proper mathematical way of describing this, is the total derivative of f is less than or equal to 0. That means f is decreasing. In the physics literature, people commonly talk about the Lagrangian variables, so they use this small ddt, whereas here in fluid mechanics we are finally going to relate it with Eulerian variables. So it will eventually be an expression which will be the total derivative. So the representation difference depends on whether we are considering the Lagrangian variable or the Eulerian variable. I did not want to mix it up here and just try to adhere to the physics description, and that is why I use this simple ddt. But when at the end we will be writing the expressions in terms of the flow field, etc., we will keep in mind that in terms of Eulerian variables this will be capital ddt. So we are finding out the derivative and setting it up less than or equal to 0. So you can just break it as chain rule. df dt is like df d phi into d phi dt, and df d phi is related to mu, the chemical potential. So mu into d phi dt is less than or equal to 0 for a dynamic system. This can be satisfied if we set up d phi dt is equal to minus m into mu, where m is positive, because if you replace this with minus m into mu, this becomes minus m into mu square. If m is positive, that ensures that it is less than or equal to 0 for all cases. This m is absolutely a phenomenological parameter which has nothing to do with the physical world, and in phase field model it is called as the mobility parameter. Now, if you write it in terms of the Eulerian variables, you can break it up into the usual unsteady and the advection terms, and this therefore becomes a convection diffusion equation in CFD terminology, where you have advection, unsteady term, advection term, diffusion term, and a source term. So you can cast it in the form of like energy equation, etc., in any CFD code, and this is known as Allan-Kant equation. So it can be in principle very easily coupled with any CFD code that anybody is working with. This is a great advantage. Any second order nonlinear partial differential equation expressed in such a form, convection diffusion form, is very appealing in CFD world because it can be accommodated by standard CFD algorithms. And this model, the so-called Allen-Can model, was traditionally employed and still being employed to solve many situations in material science, including phase separation, solidification, etc. However, every method has, if we do not call it disadvantage directly, has certain restrictions. The restriction is that while developing this algorithm, we never enforced mass conservation. Or in an incompressible system, mass conservation is equivalent to volume conservation. But in a real physical system, if that is not ensured, it gives rise to many problems. For example, if you see this classical droplet problem, you may see that this numerical computation is advancing nicely, but the droplet is shrinking, which is unrealistic because the droplet volume should be conserved. It may change its shape, but without changing the volume. So the question is how this can be enforced. So this is enforced by an additional term with a Lagrange multiplier beta to ensure volume conservation, but the Lagrange multiplier itself can be calculated from the free energy. So it is possible to obtain a modified version of the Allen-Can equation with another parameter, and calculation of that parameter itself is an implicit part of the problem, which makes it in pen and paper fine, but when you numerically compute it extremely challenging. This is known as conservative Allen-Can model. So in principle, absolutely fine. Computationally not so easy to implement. To get a simplified computational picture, further advancement appealed to this model, which is known as Can-Hilliard model. So here the total derivative is expressed as minus total derivative of phi is expressed as minus of divergence of a flux of phi j, which is very similar to any other convection diffusion equation, and the flux of j is expressed as minus of the mobility times the gradient of the chemical potential. This is partially physics based and partially one can say phenomenological. This mobility parameter was it is phenomenological. It is representative of a diffusive phenomenon which we just saw in the previous slide, and the gradient of phi, it is reminiscent of the fact that the transport of phi is governed by the chemical potential gradient, just like the transport of heat is triggered by temperature gradient, the transport of mass is triggered by concentration gradient, the diffusive transport. Similarly, the diffusive transport of phi is governed by the chemical potential gradient. So if we put that all together and write an expression for phi here, the implicit dependence of phi on f, mu on f and f on phi gives rise to an equation which is conceptually convection diffusion, but it's a fourth order nonlinear partial differential equation instead of a second order. So that is the real challenge in the CFD world, because CFD scientists or engineers are more accustomed to solving up to second order partial differential equations, linear, nonlinear, whatever, but not fourth order. So there are special algorithms for this that need to be coupled. I will not discuss this today because today is a sort of a first overview lecture on this topic. But in principle, there are well-established algorithms on this which are different from the second order PD solver solver algorithms which are there in the CFD world. The most interesting thing is that whatever may be that equation, second order or fourth order, we get an expression or a solution for phi. How we couple that solution for phi with the Navier-Stokes equation is we use a body force shown by the red color in this slide, which itself is a function of the gradient of phi. So it is although it's represented as a body force, it is also like a continuum surface force where it distributes over the interface. And in a situation where the phenomenon is driven by surface tension, it physically represents the effect of the surface tension. Various properties like density, viscosity, etc. in this model can be interpolated as a function of phi. There are various interpolation schemes. I mean, I have just shown a simple linear interpolation. It might have its own issues, this simple arithmetic mean representation, and there are more other different interpolation schemes. There are despite the complexity of the method, there are clear advantages because of which this method is now advancing even in the CFD world. So think about a physical situation which is significantly more challenging than a droplet, where you consider a biological entity like a biological cell. Cell in biology is a very complex entity which has its membrane, which is uniquely deformable, having complex biological constitution and morphology, and extremely complex activity which is not common in inert material world. Even the mechanical aspect is very complicated, but in between droplet and cell there is a conceptual premise called as vesicle, where the two fluids, unlike droplet, are separated by a membrane which is made of a phospholipid bilayer analogous to a cell membrane. Why I say analogous is not, this analogy is just conceptual analogy. It is not that it is like a cell, but summarily you can say that a small balloon filled with water, which is somewhat a different type of model than a droplet. So you, instead of a fluid-fluid interface in a droplet, you have a membrane fluid interface, and for that the phase field model has to be extended to consider the curvature and the bending of the interface, for which there are additional free energies, and there is an extra term added to cancel the surface tension which is there in a droplet carrier phase interface, which is not there for the vesicle. So all these can be accommodated in the free energy, and the modified momentum equation will have body force where you have these additional effects due to the membrane fluid interface in a vesicle. Why I am showing you this formulation is to give you an idea of the generic nature of the phase field method, where more and more complexity can be accommodated by adding more and more terms in the free energy. That's all is my intention, rather than getting into the details of the derivation. Once you have the phase field model, the continuity and the momentum, let us consider a simple case where you do not have too much of additional complications by additional source terms. Still, this minimal skeletal form you have to solve in the purview of the coupled Cahn-Hilliard-Navier-Stokes model. And this physical insight translates into numerical implementation very carefully if we normalize the relevant terms in terms of the non-dimensional parameters, which are summarily the CAN number, which is the interfacial length scale epsilon by the length scale of the physical problem. So this depends on the interfacial resolution that you take for your CFD, that is in your hand, and length scale of the physical problem. Anybody who is solving a physics-based problem will know. So in that way, one can set it up. The Piclet number is the advection to diffusion of the phase field variable, and the capillary number is the ratio of the viscous and the surface tension force. For numerical implementation, these non-dimensional numbers are very, very critical, because the convergence to a physical or a physically acceptable solution depends on whether your interface is sufficiently thin to approximate the macroscopic sharp interface limit. The CAN number value, which leads towards a situation where that convergence of sharp interface can be attained, is very similar to what we do out of a grid independence trial in a nonlinear problem in traditional CFD. That grid independence is similar to CAN number independence, because the epsilon is representative of the grid structure at the interface. Typically, for the droplet problems, from the vast body of literature, it is observed that a choice of CAN number around 0.01 is found to give CAN number independent solution. This is not a common rule. It has to be standardized with each and every type of problem, just like how we have to standardize the grid independence for any nonlinear CFD problem. Now, what it means is that, see, the resolution of the interface is very critical. So you have to commonly employ about 8 to 10 grid points at the interface. This is a common thumb rule to resolve the interface. So if you, as a guidance, look into the tan hyperbolic profile that smoothly transits the phi value from -1 to 1, that transition takes place with a non-dimensional, with a non-dimensional thickness of around 4 CAN number. So if you keep about 8 grid points around that, so typical mesh size for that would be 4 into CAN number divided by 8, or CAN number divided by 2. So this is a rough guidance of choice of grid size at the interface. So this is very, very important, and this is where actually physics comes in the computation, because if somebody is not aware of this physical background, it is possible that it is just like the boundary layer theory. So without knowing boundary layer theory, one can solve a CFD problem, but then the idea of how much the boundary layer thickness could be for a physical problem and how that should be resolved, that may not come with the CFD implementation. It is very similar to this interfacial meshing for phase field. The other parameter is the mobility parameter. It still remains as a soft parameter because it is not at all a physically based parameter. So in no way that you can measure it from macroscopic experiments. The choice of M has to be such that for certain benchmark problems, it has to be standardized with other solutions which are already benchmarked in the literature. For large enough M, the diffusion of phi is very strong, which maintains a constant interface thickness, which in a way is numerically welcome, but it also leads to large diffusion and deviation from mass conservation, which is a critical problem. So you might argue that, well, we have a continuity equation that should conserve mass. So why are we bothered about this? So the continuity equation conserves about the mass of the overall domain because we are having a single domain formulation, but individual phase mass is not conserved. And as I told you that if this is not carefully taken into consideration, very commonly in careless computations, people observe spontaneous shrinking of drops. So this has to be arrested by using not very high values of m. So these two aspects have to be balanced, and typically this balance has been achieved in the literature with values of m ranging from 10 to the power minus 2 for can number of the order of 0.01. Again, this has to be standardized and benchmarked for every problem, and it is not a universal representation of the picture. The other aspect which makes the phase field method so much appealing is that there are many scenarios in, for example, the contact line motion related problems in fluid mechanics where the no slip boundary condition has to be relaxed at locations over microscopic distances from the solid boundary. Otherwise, the contact line cannot move. In a continuum description, that is often to be imposed by a slip type of boundary condition, and that means that one has to give an ad hoc slip velocity until and unless you do a molecular simulation and understand the molecular nature of slip. That itself is a very tedious job. In the phase field model, you can, on the other hand, give a boundary condition on the contact angle on the solid boundary, which can be obtained by simple experiments with goniometer, and then that information propagates the contact line without needing to give any artificial slip boundary condition at the interface. So with all these features, we will give some examples before concluding this presentation, and these examples could broadly relate to problems where the exact profile of the interface is of great importance, like solidification or crystallization of materials, contact line motion, etc. And also some other problems where the phase field simply acts as a numerical tool to simulate multi-phase flows, and the exact detailed topology of the interface is not that important. So in that connection, I will show you glimpses of certain results of numerical computation done by mostly my former and present students. Some of them are already faculty members in other institutes. So this problem is the motion of a droplet in a microchannel under oscillatory flow. It is very important to understand such motion, considering that typical biological flows, for example, flow of blood, is having a pulsatile characteristic. So we can see this simulation, and I would not like to get into the details of the results, but I mean, it is very important to see how the droplet trajectories differ for different Strouhal numbers, which are dimensionless frequencies, and we can compare the amplitudes with the amplitude of the imposed pulsation and see whether it is near resonating motion or far away from resonance. So these are interesting situations. That particular problem as well as the problem of sandwich drop in a confined microchannel. I mean, extreme confinement in a sense that, not that the droplet is within the microchannel, it is completely sandwiched. So the order of the droplet dimension is of the order of the channel, and you can clearly see that there are two different regimes based on the contact angle at the surface. One, small contact angle, which means that it is highly wettable surface, and then if you have a shear that is imposed, a part of the droplet adheres to the surface and another part gets separated, and that process takes place via necking morphology, and this is called as pinch off. Whereas for large contact angle, it is there is the very little affinity between the droplet and the surface, so with shear it gets completely detached without leaving a footprint on the surface. So this is a pinch off regime and this is a detachment, and there is a critical condition at which there is a transition from this pinch off to the detachment. This can be very carefully computed by numerical simulation using phase field, and these studies were implemented by my former PhD students, Dr. Debabrata Dasgupta, who is currently an assistant professor at IIT Delhi, and Dr. Kaustubh Choudhury, who is currently an assistant professor in NIT Rourkela. The situation can get more complicated as we apply additional fields like electric field. So electric field driven multi-phase problem is very important practically, because one of these fluids may be conducting and the other fluids may be non-conducting. So the conducting fluid can be carried by or can be transported by the electric field. The non-conducting fluid may also be transported passively via transfer of shear across the interface. So although it is non-conducting, it may be passively transported via the stress at the interface, which is a combination of the electrical stress, which is known as the Maxwell stress, and the hydrodynamic stress. So we wanted to solve this problem where you have a patterning of surface potential, which nowadays is possible by microfabrication technology. So in a simple configuration, it is possible to get interesting vortex structures in the flow, where these vortices are locally induced to have good micro mixing. This micro mixing is very critical because in low Reynolds number flow typical to microfluidics, mixing is not very easy in the absence of turbulence. This particular problem was solved by my former PhD student Dr. Udipto Ghosh, who is currently an assistant professor at IIT Gandhinagar. I also would like to represent a problem of complex interfacial or I would say contact line motion, where there are two fluids. One is displacing the other in a capillary or a microchannel. With an electric field, the interface is initially stable, but it gets destabilized and broken up, which is of course for a given electric field dependent on the ratio of the viscosities of the two phases. So this interfacial instability in the presence of electric field is very interesting, and we captured this. This problem was solved primarily by my former PhD student, Dr. Pranab Kumar Mondal, who is currently an assistant professor at IIT Guwahati. So with all these problems and the basic background that I have presented, the summary that I want to arrive at is the phase field method has, of course, its own advantageous features. It doesn't require explicit tracking of interface. It is thermodynamically generic and does not require any calculation of interface curvature. And the thermodynamics can be represented by either Allen-Cahn or Cahn-Hilliard dynamics coupled with the Navier-Stokes equation. There are still numerical challenges related to interface thickness and mobility and mass conservation and so on. But once these are resolved for a given problem, by suitably incorporating different free energies, this method can be used to address biological systems which are inherently driven by gradients of free energies. So complex problems in medical and the biological world, which could not be solved by CFD computations, could perhaps be attempted in the future by further advancements of this method. So this is all what I wanted to present in this limited time. Thank you very much for giving me this opportunity of presenting this work, and I would be happy in discussing on this.
Now I would like to request participants, if you have any questions, you may ask now.
Yes, sir. It's a nice session. Just I wanted to ask you that, is there any restrictions or disadvantage of this phase field method?
Yes, I mean, lots of restrictions. I have mentioned two important restrictions. I mean, restrictions in a sense that two important careful measures that need to be taken. One is that we have to remember that we are diffusing a macroscopically sharp interface. So once we are diffusing, we want to capture a smooth transition across that diffusion layer, just like what we do in a boundary layer in fluid mechanics. So that has to be standardized for every problem, and for that a very careful CAN number independent study has to be conducted, which is not generic. It has to be specific to every problem, just like the grid independent studies in traditional fluid mechanics. That is still not very restrictive. What is the most restrictive from my own experience in working on this is the fixing up of the mobility parameter M. It is because it is a phenomenological parameter, it remains to be a tunable free parameter that for every type of application first needs to be standardized with some related benchmark problems either done by other standard computational techniques or maybe experiments which are available and reported, but benchmark experiments where experiments have been done in a very controlled environment. So with that it has to be standardized. If not, the danger is very severe because you are having issues of mass conservation. That means you have a spurious loss or gain of mass in one of these phases, and if a numerical analyst is careless about this situation, then the analyst can come up with very fascinating solutions. See, this is the danger of all CFD solutions, and legends like Professor Date will also agree that in the CFD world, because we have a chance of coming up with very nice, colorful, pictures which can impress people, sometimes it masks the physical consistency of the solution. I mean, if somebody is not careful, will not give a due attention of that and will be very impressed with the colorful representation of whatever, I mean, the interface, the streamlines, velocity vectors, whatever. So if we are ignorant about that, then actually the physical problem is not accurately solved. And in the phase field model, that is not yet standardized. There there is a third issue which I want to highlight, which I have actually mentioned but not highlighted that much, is the issue of the computational time. The phase field model may take abnormally large computational time for many other problems that are solvable otherwise, where complex topologies are not involved. So in such cases, it would be preferable to use other methods rather than the phase field. The phase field should be used in applications where it is imperative, in a sense, that the topological evolution of the interface occurs over a length scale which is very much similar, or which is very much comparable to the interfacial scale captured by the phase field dynamics. With that kind of a problem, that means in that situation, the physical scale of the problem approaches the interfacial scale, and then to capture the interfacial region, the phase field may be very, very effective because you want to resolve the physics there, which might be difficult to resolve with other methods because of the collapsing of the interfacial grids.
Okay.
So, summarily, my observation is that no method in the numerical computation world is absolutely superior as compared to others. It depends on what is your application and how you put the strengths and weaknesses of your method in perspective of that application. And if the strengths are significant and weaknesses can be overcome, then it should be used. It is true for any other method, and it is true for the phase field method also.
Okay, sir. Sir, mobility parameter n, is it depends on the fluid and the geometry also, or it is not dependent on this?
No, it is. It is. It is very difficult to say. Exactly on which it depends, because when you are solving a fluid dynamics problem coupled with the phase field, you are fixing up the mobility parameter simply by looking into their coupled solution. So their coupled solution is dictated by many things: the geometry, the boundary conditions, the fluid properties like density, viscosity, etc. So which is explicitly affecting this is very difficult to isolate, because this is not a really analytically solvable problem. So you are standardizing this via numerical computations, where what exactly is affecting the numerical computations the most, it is not so easy to isolate.
Correct. So how do we fix it? Basically, for fixing it, we need to see the certain parameter or certain range.
There are very simple guidelines. Okay. So to fix it up, as I said, there are two things you have to see. Number one, is there a benchmark problem already supported by other methods and validated extensively in the literature, which is very close to the kind of problem that you are solving? Okay. So you standardize the mobility parameter by solving that problem. Number two, you check the mass conservation of the individual phases at each and every stage and see whether your computation is strictly satisfying mass conservation. So if you are satisfied with both of these, then possibly that mobility parameter is going to work for the further advancements of the problem that you are considering.
Thank you, sir. Thank you very much. Is there any other questions from the audience side? Is there any other questions from the audience? You can write down your questions in the chat box also if somebody wants to ask.
No, it is fine. Perhaps because this is a relatively, not very well known topic in the CFD world. So yes, perhaps all the participants will take some time to look into this. The basic literature, and then if there are questions, I would be very happy to answer. And what I would request the organizers also, because these are very important topics and not well known to the CFD world. I mean, I have no issues if you can post a video of this lecture freely on YouTube, and so that I mean the whole purpose of having this workshop or these kinds of workshops is not to be restrictive, that it is just sort of attended by a few people. I mean, there is nothing very secret that we are talking about here. Yes. It's a very academic type of discussion, and you can put it up in the YouTube as a free material, so that not only the participants of this workshop, but anybody else who are known to you, or your students or your friends, or maybe some of my students also can look into it. So I would request that if you please upload this in a freely downloadable YouTube link.
Sure,
and share with all the participants as well as with me also. And
sure.
Then possibly at some time, if some of the participants have questions, we can refer to that lecture and discuss the questions, so that it becomes very effective, and this becomes a very good emerging practice in the CFD community that we have in India.
Sure, sir. I would like to request Professor Bala to give a vote of thanks to Professor Suman Chakravarty, sir.
With this, I would like to thank our esteemed guest today, Dr. Suman Chakravarty. Thank you so much, sir, for sparing your time and letting us the topic of multiphase and the methods you have discussed. I personally feel that the way you are describing it, let us say if somebody is going to refer some online literature and this, so this is very helpful. And at the same time, I would like to thank Dr. Anil Date sir for attending this session, and to all the participants also. Thank you so much, sir.
Yeah, thank you so much to all of you, and my best regards to Professor Date. Thank you, sir, so much, and it has been my honor in seeing you not just at the beginning, but you have been throughout this relatively long presentation. And sir, please stay safe and in good health, and we are all looking forward to guidances of legendary professors like you. Thank you all very much, and goodbye for now.
Thank you very much, sir. Thank you. Bye-bye.
Thank you, sir.
Okay.
See you.
So the next session will start at 11:45. So our session expert is Mr. Siddharth Borkatke. He's from Design